Hello, can you guys hear me?
Yes, sir.
Okay. Alright. Okay. Are you able to see the slides?
Yes, sir.
Okay. Okay. So, how many are we? Okay. So we have 11 people in the class. All right. So, any questions on the surprise quiz? It was fairly straightforward, and I think most of the class did pretty well. I think the class average is probably 9 or close to 9. So, so most people have done well, which means, of course, that you've understood uh, uh, the concepts. But the one thing that I felt that people had probably not got most of it correct was the question on hydraulic head. So the hydraulic head is the summation of uh, the gravity head or the elevation head and the suction head. So most people had, I don't think most people got that one. And then the other one being the initial abstraction thing. I think only a small percentage of the class got that question right, probably 20-30%. Anyway, but so when you got back the assignment, did it tell you what the correct answer was, or how does this Google Classroom work? Can anybody just quickly tell me, when you get back the assignment, the corrected graded assignment back, what information is shown to you?
Only the marks, sir.
Or the total or the marks per for every question?
The total, sir.
Only the total is shown. Oh, okay.
So when we ask for the responses copy, then it will show like which is correct, and as soon as we submit, if we press on the score button, we'll get only the MCQs part which is correct and wrong, and the descriptive ones are later corrected by you.
Now that I understand, but I'm saying when I returned the graded assignments back to you, did it show you the breakdown? Like, for example, let us say you've got 9 out of 10. Did it show you where you lost that 1 mark?
Yes, sir. But we need to visit the form again so that we can know, sir, where are we lost marks.
Oh, you have to visit the form again.
Yeah.
Okay. Yeah, well, I didn't know about this. Anyway, so maybe I can make the answers available online, the answers to each question, and that will probably solve the problem. Okay. All right. So today we are going to this is going to wrap up the lecture on the chapter on infiltration. We'll try to finish off very quickly. Now, this portion, I'm not going to spend a whole lot of time, this measuring infiltration. Did you learn about infiltrometers in your soil mechanics class?
No, sir.
No. Okay. The idea is very straightforward. So let me just very quickly go through that. So, so when I want to measure infiltration of a given soil sample, one of the, so far we were estimating, remember that. Okay. So now this, if I were to go into the field and say, okay, I have a certain kind of soil over here, let's find out what the infiltration rate of this particular soil is. Okay. So then what is typically done is you have what is called a simple infiltrometer, which is basically a cylindrical core of about 30 centimeter diameter and about 60 centimeters long, which is driven into the soil, okay, to a depth of about 50 centimeters into the ground. Okay. So then when it is driven in, then we start pouring water at the top, okay, and bring it to, let us say, a level of 5 centimeters above the land surface, right? So you understand what I'm saying? Oh, 1 second. Just hang on for a second. 1 second. I'm back. Yeah. So what I'm trying to say is, you drive this looks like my Bluetooth isn't working. Okay, sorry once again. Just hang on. Okay, yeah. So we drive this into the soil. Now it's working. Okay, yeah. Sorry. Okay, so we drive this into the soil up to a depth of about 50 centimeters from the land surface. Then we start filling up water, you know. So this is this land surface. Okay, so this red dotted line that I've drawn, that's the land surface. And then we pour water maybe up to a height of about 5 centimeters above the land surface. And then we let the water infiltrate. What we do is we keep adding water at some intervals of time to ensure that the water level always stays at 5 centimeters, right? You can think of it as some kind of a constant head permeability test. Okay, so what's happening, I keep maintaining water at that 5 centimeter level. Okay, and so the water keeps infiltrating in. Okay, so initially when the soil is, you know, not completely saturated, you can imagine that you will have to add water frequently to keep it at 5 centimeters, right? So you keep adding water to maintain the water level at 5 centimeters. Initially, naturally, since the soil is, you know, relatively dry, you have to keep adding water frequently, right? So let us say every 5 minutes you add, you know, 20 milliliters of water or 50 milliliters of water or whatever it is. So for example, if every 5 minutes I'm adding 50 ml of water, then my infiltration rate is 50 ml per 5 minutes, right? So I can very easily estimate the infiltration rate depending on the amount of water that I add in the time interval. Then I know how much infiltration has happened in that time interval, right? So then you keep doing this, and then you get an you know, an infiltration capacity versus time plot, right? What you do is you keep doing this until you get a uniform infiltration rate, right? Remember this. So the plot will look something like this. I have time on the x-axis and I have the infiltration rate. Initially, I'll get some high value, and then I'll get a something as the experiment proceeds, it will get a lower and lower value. Eventually, after a long time, maybe you start getting more or less a uniform rate. Maybe it may take 2 or 3 hours, depending on the kind of soil that you're looking at. So you continue this experiment for a long time until you get some kind of curve like this. And then that tells you what the infiltration rate or your infiltration capacity of your soil is. Okay. So now the question is there any disadvantage of this approach? There's a hint in the figure that you see over there. There's a hint that there is some disadvantage to this technique. Can anybody figure it out? Yeah, just look at the bottom. You see all these arrows pointing out the direction in which water is moving. So far, when we discuss infiltration, we always assume that the water is moving vertically down, right? But in this kind of a setup, water can move in all directions, right? So if I imagine this in plan view, if this is the ring that you've drilled into the ground or driven into the ground, the water is free to move in all directions, including downwards, right? So in plan view, it'll radiate outwards, and it'll also continue to move downwards, of course, right? So you see the arrow in the middle is indicating that water is moving downwards vertically with gravity, but it can also move through the sideways. So that is one of the disadvantage, is that infiltration is not only happening in the vertical direction, it is happening in kind of, it's also happening radially simultaneously um, with along with the vertical direction. So you may tend to overestimate the infiltration, right? That's what this test does. Okay, so that is what is called the simple infiltrometer, right? A simple ring driven into the soil, and you do this kind of a simple constant head permeability test, right? Okay. Now to overcome this disadvantage, what is sometimes done is we use a slightly more sophisticated technique, which is called a double ring infiltrometer. Okay, I'll just show you what it looks like. So instead of having one ring, you have two concentric rings. Okay, so if I look at it in plan view, it will look something like this. There'll be one ring on the outside and then another ring on the inside. And so this entire setup is driven into the ground. Okay, consisting of these two rings, and then the dimensions are given. These are typical values. Okay, 30 centimeter diameter inner ring diameter and 60 centimeter outer ring diameter. Okay, same thing is done. You drive it in to certain depth, and you maintain a water level of maybe 5 centimeters above the land surface. Now if you notice, the outer ring is allowing water to infiltrate in all directions, but the inner ring, simply because I have an outer ring which is kind of preventing water from moving in the radial direction, the inner ring will only allow water to go downwards. Do you agree with that? More or less. Okay, it may not be perfect, but this outer ring is somehow preventing the water in the inner ring from moving radially outwards. So it is only allowing water to infiltrate in the vertical direction, right? So I have these two concentric rings. The outer ring prevents the spreading of the infiltrating water, right? The outer ring prevents the water from spreading in the inner ring. I mean, so the outer ring is preventing the water that is poured into the inner ring from spreading. Okay, so then therefore you compute the infiltration rate only from the inner ring, right? You maintain the level in the inner ring and the outer ring at 5 centimeters, but you only compute the infiltration rate from the inner rings, the volume that you add to the inner ring. Okay, so it's a very simple procedure. I don't want to spend more time talking about this. I guess you can all imagine how this kind of a system will work. Okay, now overall, in general, with this kind of an infiltrometer, whether it is simple ring or the double ring, can you think of any other disadvantages? Okay, I'll just mention a couple of them. One is that this may only represent what is happening, what the property of the soil is at that particular point. So it's a point measurement. You may be interested in a watershed of a very large area, but if you're going to use this infiltration ring to give you an idea of what the infiltration rates are, you will have to do a number of tests, right? So if the larger the area, the more the number of tests that you'll have to do to understand how infiltration rate varies spatially and so on. Okay, so naturally it's a cumbersome procedure. Okay, you'll have to do it at multiple places, and the larger the area, the more the number of tests that you have to do. Okay, that's one disadvantage. The other disadvantage, okay, now this is a little bit you might not appreciate this as much, is that it ignores the impact of a raindrop falling on the ground. Okay, so if you look carefully at the land surface when a rainfall event starts, right, you will notice that the land surface gets disturbed because of the raindrop that's falling has got certain kind of it creates an impact on the surface. It may disturb the soil at the surface. Okay, whereas this approach kind of ignores that impact. And remember that when your raindrop creates some kind of a when it falls and creates it may create some instead of having a given porosity of the soil, it may increase the porosity locally. Okay, which may facilitate water to infiltrate a little bit more easily. Okay, because of this impact that the raindrop has on the soil. Now naturally this kind of an impact, it may not be very significant depending on the type of soil. If it is, for example, if it is a sandy soil, this raindrop impact may be relatively less. if it's a more of a silty or a clayey kind of soil, this impact may be relatively more. Okay, and then it also depends on the kind of slope that you're looking at and so on. If it's a relatively flat slope, then this raindrop impact may not be as much as if it were a relatively steeper slope. Then you may also have a little bit more of an impact. But this impact, uh, although it's sometimes important to consider it, I don't think it's all that important a factor when you're looking at a relatively large area. Okay, but it does play a role. Okay, that's just something that you have to keep in mind. And the other thing is that when you do these, when you drive this infiltrometer into the ground, you're disturbing the soil sample. It is not how the natural soil will be. Just the act of driving it in will do some amount of compaction and so on, which may again alter the soil characteristics, and it may change the way the soil responds to infiltrating water. Okay, so that's another disadvantage that infiltrometers have. All right. Okay, so let's move on now. So to kind of, I'm moving on in this direction with a particular emphasis. So now we've seen an infiltration meter, or the infiltrometer in the previous slide, which is essentially a point measurement. Okay, and then we've also discussed in the previous classes about all these different equations, the Green-Amps equation or the Horton's equation, the Phillips equation, and so on. These kinds of methods for measuring infiltration are relatively useful when you're looking at a local or a particular location where you know the soil properties, right? I know that the soil that I'm encountering at this point is a sandy soil or a clay soil or silt or whatever it is. If I know all that, then using these approaches, whether it is Green-Amp or Horton or Philip, it's relatively feasible, assuming that I know the soil properties. But if you're interested in a relatively larger area, okay, let us say you are interested in the whole catchment, okay, then you need some kind of a more simpler approach that is valid for an entire larger area. Okay, instead of having knowledge about point locations and how the soil properties vary spatially, you may need to come up with a more simpler approach which can be applied for a larger area. Okay, so that is where we come up with this notion of what is called an infiltration index. Okay, so this infiltration index, sometimes there are a couple of indexes, but the most popular one is called the phi index. Okay, so this symbol that you see over here is called the PHI. It's the Greek letter phi. Okay, some people say phi. I prefer to say phi. Okay, so this phi index is basically the average infiltration rate for a given area. Okay, for a large area, if I can somehow come up with the average infiltration rate for that large area, then that is what I'm going to call my phi index, which can be useful to understand, the runoff that will be generated from a catchment, for example, given a certain rainfall event. Okay, so this phi index is so let us very simply define this. This phi index is the average rainfall above which a rainfall volume equal to runoff volume. Did you understand that? It's a little bit. So let us say I receive 10 centimeters of rainfall. Okay, if I receive 10 centimeters of rainfall over a duration of, let's say, 8 hours. Okay, now this 10 centimeter may be distributed in these 8 hours in the form of, the first 1 hour you may receive half a centimeter, the next 2 hours you may receive 4 centimeters, and so on, right? So this over this 8 hours, it is not uniformly distributed. It is distributed at different rates. Every 1 hour or 2 hour interval may have different rates of different intensities of rainfall, right? So maybe in the first 1 hour, you may receive only a little bit of rainfall, and none of it may become runoff, right? So if I receive a certain amount of rainfall in a given duration, and none of it becomes rainfall, that means what? All of that if none of it becomes runoff, that means all that rainfall has become, what has it become?
It infiltrated.
Infiltration. It has become infiltration, right? So this phi index is basically saying this is the average rainfall such that any amount of rainfall that is greater than that average, right? All of that volume that is greater than that average has become runoff. Okay. Is this, maybe I'll show you a figure that might explain this a little bit better. So look at this figure. Okay. So on the x-axis I have time, and on the y-axis I have the rainfall intensity as a function of time. Okay. So in the first 2 hours, so look at this. So in the first 2 hours, you got 0.5 centimeters per hour of rainfall. The next 2 hours, you get 1.25 centimeters per hour. The next 2 hours, you get 2 centimeters per hour, and so on, right? So this is what is this kind of a curve called? What is this kind of a plot called? It's over here.
Hytograph.
It's a rainfall hytograph. Okay. So it is plotting the intensity, rainfall intensity as a function of time, as a bar chart. Okay. So this phi index, let us say this line that is drawn over here is the phi index. Okay. So what it is saying is, it is that average rainfall above which, so whatever is above that shaded portion, that portion of the rainfall has all become runoff. You understand this? Right? So if I know, so let us say in this case, the phi index looks like it is about 0.6 centimeters per hour. Okay. So let us say the phi index is 0.6 centimeters per hour. Okay. Only if I receive rainfall intensity more than 0.6 centimeters per hour, it will result in runoff. Any rainfall that is less than 0.6 centimeters per hour will simply become infiltration. Okay. So this is an average way of looking at the relationship between rainfall and runoff. So does this figure explaining clearly what that first sentence is telling you? The average rainfall above which rainfall volume equal to runoff volume. Okay. So this entire, okay, let me just draw it over here. So this, whatever I'm shading in red is the rainfall that has become runoff. The remaining portion, the shading that says losses, or it is shading in black, that is all the rainfall that has become infiltration. Okay, as simple as that. But to know this, you need to know the total runoff volume and the rainfall hytograph. To be able to find out what this phi index is, you need to know both the rainfall hytograph and the total runoff volume. Okay, for a given watershed or for a given catchment. Okay, right. So the portion of the rainfall that is in excess of this phi index. Okay, there are lots of terminologies that are available for this. Sometimes it is called excess rainfall. Okay, sometimes, oops, sorry. Sometimes it's called excess rainfall. Sometimes it's also called effective rainfall. Some people also call it rainfall excess. Okay. So the portion of the rainfall that is greater than the phi index, right? This red portion, the red shaded portion that I've drawn over here, that portion is called, there are different names for it. Sometimes it's called excess rainfall or rainfall excess, or effective rainfall, or another terminology used is direct runoff or total runoff, something like that. All kinds of names are sometimes used to refer to this rainfall that is greater than the phi index. Okay, so this is the notion of the phi index. Okay, any questions on this?
No, sir.
Yes. No questions? All right. So let's, it becomes easier to understand once you solve a small problem on this, then it'll give you a much better idea of what this. So I'll just explain the procedure used to estimate the phi index. Okay. Let's go over that. Right. So the procedure for the calculation of phi index is like this. So consider a rainfall hytograph, which consists of a rainfall event of duration d hours, which is divided into n time intervals delta t, right? So n times delta t equal to capital D, right? So in the previous example, you see, what is that? So the total duration of the rainfall event is 14 hours, and it is divided into 7, 1, 2, 3, 4, 5, 6, 7, 7 pulses of 2 hours each. Okay, right? So you see the duration 0 to 14 hours, and it is divided into equal intervals of 2 hours. So there's 1, 2, 3, 4, 5, 6, 7, 7 durations of or 7 time intervals of 2 hours each, right? So in this case, capital N is 7, delta T is 2 hours, and capital D is 14 hours, right? Fairly simple. Okay. Now the total rainfall that is received during this rainfall event is P equal to, total rainfall P is given as sigma II. Okay, sigma II. Now you can very easily understand what II is. What is I? What is this capital I? Intensity, right? So the subscript small I goes from 1 to n, right? So like in the graph that I had shown previously, capital N was 7 and delta T was 2 hours. Capital I is simply the intensity in every interval of 2 hours. In the first interval, you had an intensity of, I'm sorry, in the first interval, you had an intensity of 0.5 centimeters per hour. The second one, it was 1.25 centimeters per hour, and so on. Okay. So this II is basically the intensity of rainfall in every given time interval. Okay. So this is fairly straightforward. I don't think this really requires any explanation. Okay. Now let us assume that the duration of excess rainfall is given as TE, T suffix E. Okay. And the total runoff depth is given as R suffix D. Okay. Suppose I know that because of this kind of a rainfall event of D hours, which produce a total rainfall of P centimeters. Okay. Let us say that this rainfall of P centimeters in D hours produced a runoff, a total runoff depth of R suffix D centimeters. Okay. Usually we refer to it in centimeters or millimeters. Okay. Now, how do I get a runoff depth instead of a runoff volume? How would I convert a runoff volume into runoff depth? First of all, how would I get runoff volume? Let us say this is my watershed. Okay. And this is the stream that is draining the watershed, which may have multiple whatever tributaries and so on. Let us say at this point, sorry, okay, at the outlet. So this is the outlet, right? At this outlet, I measure the runoff. Okay. I measure the runoff as a function of time. Okay. Rainfall starts at T equal to 0 and ends at T equal to D hours. I sit there and I wait for all the runoff to happen. It may take more than D hours. It may take, let us say it takes 2 D hours. I sit there and measure all the runoff that's coming out and convert it into a volume. Okay. I can convert the total runoff that happened into a volume. Can I not do that? Very easy. If I know the rate of runoff and I measure the runoff rate at multiple points in time, I can compute the volume as simply the integral of that runoff volume. Sorry, of the runoff rates as a function of time, right? I compute the runoff volume. Now I take this runoff volume, which may be in units of, let us say, meter cube. Okay. And I divide it by the area of the catchment. Okay. So this catchment, let us say it has an area of a kilometer square. Okay. I take that runoff volume that I've obtained, divided by the area of the catchment. I will get this number, runoff depth. Is that okay? Right. So what I've done is I've taken the total runoff volume that was generated by the catchment, divided it by the area of the catchment, and represented my runoff in terms of depth. Okay. So it's fairly straightforward. There's nothing very complicated about this. Okay. Now here, why am I saying that the duration of excess rainfall is TE? Why am I not saying that the duration of excess rainfall is the same as capital N? Why am I not saying that? Because
Because
yes, yeah.
sometimes the rainfall intensity might be lower than the.
Yeah, so let's just go back to the previous slide. That will explain it very clearly. Okay, so look at this one. Although I have rainfall starting from 0 to 14 hours, the rainfall from 0 to 2 hours did not result in any runoff, right? Because it was less than the fee index. Similarly, the rainfall from 12 to 14 hours did not result in any runoff, okay? Because it was lower than the fee index. If you're using this fee index approach to estimate the runoff from this catchment, then the first 2 hours and the last 2 hours are not contributing anything to the runoff. Okay, that's the assumption behind this approach. Okay, so therefore, although the duration of the rainfall event in this case was 14 hours, the duration of excess runoff was only 8 hours. 10 hours. Correct? The duration of the runoff was only 10 hours, not 14 hours. The rainfall lasted for 14 hours, but only 10 hours produced runoff. Okay, that is the assumption in this approach. Okay, so let's just, yeah. So that's why I deliberately denote it as TE. Maybe TE is equal to N, but it may not be equal to N. It may be less than N also. Okay, so that's something that we have to keep in mind. Okay, so now from the previous slide and from what you have seen so far here, can I write an expression for relating RD and P and phi, this phi index? I'm going to write it. It is simply P, which is the precipitation, the total rainfall, minus phi times TE equal to RD. Do you agree with this equation? Just go back here to the previous slide. This capital P is the total rainfall received in the entire 14 hours. Okay. How do you obtain that? You multiply the rainfall intensity by the delta T for each time step, for each time interval. So the intensity here is 0.5 centimeters per hour. The intensity here is 1.25. The intensity here is 2, and so on. You multiply each of them by 2 hours and add it all up. That gives you the total rainfall. I subtract the phi index by the duration of excess rainfall. So in that case, it was, what was it, 10 hours, right? Capital N is 14 hours, but TE is only 10 hours. So if I know the phi index and multiply it by TE, the duration 10 hours, that should be equal to the runoff depth RD. Is that not correct?
Sir,
Now yes.
sir, but the total rainfall would also contain the rainfalls in the time of 0 to 2 hours and 12 to 14 hours.
Yeah,
So
yeah.
we are not removing that because this RD is the depth only from 2 hours till 12 hours. No, I mean,
No,
there'll
no, no,
be
no. See,
extra rainfall.
no. See, beforehand, this runoff depth that you've computed has nothing to do with the time. You just sat at the outlet and measured all the runoff that came out. Okay, and that you converted that. I mean, let us say you had a big tank at the outlet and you just filled that tank. Okay, just imagine this. Imagine that at this outlet, I had a big tank, and you let all the runoff that was generated here just fall into that tank. And you could, you knew the shape of the tank. You could measure the depth of water in the tank. You measured the volume. You knew the volume. You divided it by the area of the catchment, and that gave you runoff depth. It has nothing to do with the duration. Okay, so the total precipitation may have been 10 centimeters, and this total runoff may have been 7 centimeters. Sorry, runoff depth may have been 7 centimeters. Does that answer your question? See, beforehand, I don't know. When I'm trying to solve this, I'm trying to solve for phi index also. I don't know the phi index. I don't know the TE. All I know is the total amount of rainfall received P and the total runoff depth that was obtained from the catchment RD. I don't know phi, I don't know TE. Okay.
Yes.
So naturally, it's one equation. I have two unknowns. There's no way to do it. We resort to a trial and error method to estimate the phi index. Okay. So I'll describe this trial and error method briefly, and then we'll solve a problem. Okay. So that will make it much more clear to you. Okay. We will assume m number of pulses. When I say pulses, I mean time intervals. Okay. M number of time intervals contribute to the excess rainfall. Okay. There are n time intervals in total, out of which I'll assume that only some number m contribute to excess rainfall, and m must be less than or equal to n. M cannot be greater than n. Okay, it has to be less than or equal to n. You agree with this? I will assume that some number of time intervals contribute to excess rainfall. M less than or equal to n. I'll make that assumption. Okay, then I will select out of all the time intervals, I will select m number of pulses in decreasing order of rainfall intensity. Right? So if you go, okay, I don't want to keep going back to that slide. Okay, out of those n pulses, I will select the top m pulses in decreasing order. Okay, select m pulses or m time intervals in decreasing order of rainfall intensity. So if m is less, so in that previous example, n was 7, right, and m was 5. Okay, so I only pick the 5 time intervals which has the highest rainfall intensity. I neglect those 2 small intervals that don't have intensity greater than the phi index. Of course, we don't know the solution beforehand, but I'm just talking about that in general. Okay, we don't know the solution beforehand. Okay, so we select m pulses in decreasing order of rainfall intensity. Then we find a value of phi that satisfies this equation, RD equal to II minus phi into delta T, I going from 1 to m. Is this clear? Is this step clear? You find a value of phi that satisfies this equation, RD equal to sigma I going from 1 to m, not 1 to n. Okay, you're only counting those rainfall events. I see your question now, Aditya. You're wondering why it was this p over here. Okay, this
Yes,
equation,
sir.
you're right. Yeah, this is a little bit misleading. I'm sorry. Now I understand why you said that. Okay, fair enough. Yeah, so this is the second equation that I've written. That's the correct one. Okay, it's what I should have said is, in that excess rainfall duration, how much total rainfall was received. Instead of using the total rainfall P, I should have just used the, yeah, you're right. Okay, now when I see this equation, then it makes sense to me. Okay, so all right, so you just solve for this, find the value of phi that satisfies this equation, right? You already know m, you know II, you know delta T. So this is one equation, one unknown, right? So you can solve this equation, you will get some value of phi. When you get that value of phi, you count the number of pulses that satisfy this expression II greater than or equal to phi. Whatever number you get, MC, m suffix, m subscript c, should be equal to m. If this MC that you get is equal to m, then your assumption of m was correct, right? Because in the first step, you assumed some number m, right? You assumed some number m and you did this entire procedure. If at the end of it, you find that the number MC that you're obtaining is the same as m, that means you're done. But if not, then you go back and change your m and then repeat this process. Keep doing it until you arrive at an m such that MC equal to m at the end of a given iteration. Okay, it's very, very abstract. I understand that. When we solve it, it will become perfectly clear to you. Okay, we'll just we'll solve one quick problem, and then that should make it very, very clear to you. Okay, so this is the problem statement. Okay, this is coming from Professor Subramania's textbook. Okay, a storm with 10 centimeters of precipitation produced direct runoff of 5.8 centimeters. The duration of the rainfall was 16 hours and its time distribution is given below. Estimate the phi index of the storm. Okay, so that's the problem statement. So the information that's provided to you is basically what is this information? It gives you the time versus cumulative rainfall. So what kind of plot is this? This is not a hyetograph. What is this? This is not a hyetograph. This is a
Mass curve.
Thank you. Okay, so this information that you see is time versus cumulative rainfall. Cumulative rainfall. So it keeps going like that. Okay. At every delta t, the slope is the rainfall intensity for every delta t. Correct? Right. So which means in the first 2 hours, you have received 0.4 centimeters of rain. So the rainfall intensity will be 0.2 centimeters per hour. Correct? Because it's 2 hours. The next 2 hours, you have received 0.9 centimeters of rain. So therefore, the rainfall intensity will be 0.45 centimeters per hour and so on. Okay. So I'll just, okay. So now I've just rewritten this problem statement in a slightly different, I've rewritten this information in terms of pulses. So there are 8 pulses in total, coming to a total of 16 hours, right? So the cumulative rainfall, 0.4 centimeters, 1.3 and so on. This is all the same as the previous slide. So the incremental rain received in every 2 hour interval is 0.4 centimeters, 0.9, 1.5. How are these numbers obtained? This one is straight 0.4, 0.4. This one is 1.3 minus 0.4, 0.9. This one is 2.8 minus 1.3, 1.5. 5.1 minus 2.8, 2.3. 6.9 minus 5.1, 1.8, and so on. Okay, so these are all the rainfall amounts received in every successive 2 hour interval. Okay, so the third row or the fourth row is the incremental rain received in every 2 hour interval. So from that, you can estimate what the rainfall intensity was in each of those time intervals, right? 0.4 divided by 2, 0.2 centimeters per hour. 0.9 divided by 2, 0.45 centimeters per hour, and so on. Okay, it's very, very easy. I'm not going to bore you with all these details. Okay, so in the first trial, what is my capital N? Capital N is 2 hours. Okay, I assume capital M is also, sorry, oh, I'm sorry. I'm so sorry. That the delta T is 2 hours. I'm sorry. Delta T is 2 hours and capital N is 8. I have 10 intervals of, 8 intervals of 2 hours each. So capital N is 8. My limitation for capital M is that M must be less than or equal to N, right? So for the first trial, I'm assuming M is equal to 8, no problem. Okay, which means all the rainfall interval, all the time intervals are contributing to runoff. Okay, what is RD? RD was given in the previous slide. Oops, I'm sorry. RD is 5.8 centimeters and capital P is 10 centimeters. Okay, RD is 5.8 centimeters and capital P. Total rainfall is 10 centimeters. Okay, so now I've assumed that M equal to 8, which means if you remember the equation from the previous slide, RD equal to sigma I equal to 1 to M II minus phi times delta T. Is that okay? RD equal to I equal to 1 to M II minus phi into delta T. Now, I don't want to write out the entire equation, but it will look something like this. Okay, 5.8 equal to, I will write the first okay, how do I say this? Okay, I'll write this like this. Okay, what is the rainfall intensity in the first I equal to 1? It's 0.2, right? 0.2 plus 0.45 plus 0.75 and so on. Last one is 0.25 times 2 hours minus what will it be?
8 into 5 into 2.
16.5. Does everybody agree with this? What I've written over here?
Yes.
Right? all I've done is I've taken the rainfall intensities, and since the delta T's are the same, I can just add them all up and then multiply it by the delta T, right? Instead of 0.2 into 2 plus 0.45 into 2 and all that, I've just taken the 2 out common. Okay, this is all fairly straightforward. And then this one is minus 16 into 5. Why is it 16 into 5? Because M is 8 and delta T is 2. 8 times 2 is 16. 16 times 5. Right? No problem. So now this is a very simple algebraic equation. I have 5.8 on one side and I have all these numbers on the other side. I solve for the only unknown here. So I get phi equal to, I'm just writing the answer directly from the textbook. Okay, it's a solved example in the textbook, 0.263 centimeters per hour. Okay. Now what do? I go back to the table and count the number of intervals where the rainfall intensity is greater than phi index. In how many cases is it greater than the phi index? 6, right? Although there are eight intervals, in 2, the first and the last one, the rainfall intensity is 0.2 centimeters per hour and 0.25 centimeters per hour. And the answer that I have obtained is 0.263 centimeters per hour, right? So the remaining 6, 1, 2, 3, 4, 5, 6, they are greater than. So how many intervals? MC equal to 6. These are the intervals where II is greater than or equal to phi, right? That is the definition of the phi index. Those intervals where the rainfall intensity is greater than phi index are the only ones that are contributing to the runoff. I had assumed that all 8 intervals are contributing to runoff. But when I made that assumption, I'm getting a phi index of 0.263 centimeters per hour, from which I'm finding that only 6 intervals are greater than that. Okay. So therefore my original assumption of 8 must have been wrong, right? Everybody agrees this is the critical step. If you agree, if you understand this, then we can move on to the next trial, sorry. Right?
Yes, sir.
Since the phi index that I'm getting does not satisfy the condition that those many number of intervals should have rainfall intensity greater than whatever phi index that I've obtained. So therefore my assumption of 8 was wrong. So I go to my next trial. So I go to trial 2. Now I assume M equal to 7. So when I do M equal to 7, what do I have to do? I pick the 7 highest rainfall intensities. So I have to drop out. Which one do I drop out?
First one.
The first one, 0.2 centimeters per hour. I have to drop that, right? Because I have to arrange in decreasing order. I have to arrange the rainfall intensities in decreasing order and pick the top M. In this case, M is 7. And so therefore I have to drop the lowest rainfall intensity. So then again, I come back to the same expression, RD equal to sigma I equal to 1 to M II minus phi into delta T. But now M is no longer 8, M is 7. So then this equation will look like this, 5.8 centimeters equal to, I am excluding this 0.2, I'll get 0.45 plus 0.75 plus so and so plus 0.25 multiplied by, what will it be multiplied by? 2, right? 2 hours, delta T is 2 minus, what will it be now? 14 phi, thank you. So last time it was 16 phi because M was 8. 8 into delta T is 16. This time M is 7, so it will be 14 phi. Now again I have one equation, one unknown. So I solve this, I get phi equal to 0.271 centimeters per hour. Okay. So what do I do now? I again go back and compare the phi number that I've obtained and find out how many intervals does this satisfy the in how many intervals is II greater than this phi number that I've obtained. What do I get for MC? Again I get 6, right? Because this 0.25 is less than my phi index, but I included it in this computation, right? So therefore again my value of m that I've assumed is incorrect. So now I go back and do my trial 3 and say, now let's assume m equal to 6. Then what happens? Then I have to drop this number and this number, because these are the two lowest values. In decreasing order, if I select m number of pulses, m number of time intervals, then both of these will get eliminated. So I'll get Rd equal to sigma I equal to 1 to m. I'll just keep writing it again and again because that's the only way to do it. So it will be 5.8 equal to 0.45 plus 0.75 plus so on and so forth plus 0.5 times 2 minus 12 phi. By this time I don't want to bore you with it. So it's a simple equation. I get phi equal to what do I get? I get phi equal to
0.273.
Oh, you solved it. Good. Or you have the textbook.
Solved it.
Good. Sorry. Okay. So I get phi equal to 0.275 centimeters per hour. Now I go back and check what MC is. What is MC? 1, 2, 3, 4, 5, 6. MC equal to 6, which is equal to M. Therefore, I'm done. So the phi index, the answer to this problem is 0.275 centimeters per hour. Okay. So now, suppose I do this for multiple rainfall events for the same catchment. Okay, and I do this analysis and I come up with a phi index for a given catchment. What will it allow me to do? The next time I have a rainfall, right? So suppose I predict tomorrow I'm going to receive so much rainfall. Okay, in the first 1 hour I may get a rainfall intensity of so and so. The next 1 hour my rainfall intensity will be so and so. And during the course of the day I'm going to receive this much rainfall. What do? You simply create a hyetograph, and using the phi index that you have obtained from past information, your watershed is not going to change its behavior, right? If your phi index last year was 0.275 centimeters per hour, this year also when you receive rainfall, your phi index is going to be 0.275 centimeters per hour, right? Phi index is not going to change with time unless, you know, a new city has come up in that area. You've destroyed all the trees and put up a city there with lots of impervious surfaces, then the phi index will change. But assuming that the catchment has not significantly, there has been no change in the catchment. Whatever area was there previous year as forest is still there as forest this year, and so on, right? Assuming that the land use has not changed too much, then the phi index is not going to be a function of time. So if I know the phi index from my historical data, I can use that information and say, okay, tomorrow I'm going to receive rainfall of this kind of magnitudes over this kind of a duration. Then using this phi index, I can predict how much runoff will be generated. Can I not do that? Right? So it's a very, very powerful tool which allows you to understand how a watershed or a catchment will behave given a certain rainfall hyetograph. Okay, so I'm going to stop with that. I'm going to talk about, you might have seen, I don't know if you received an email. I've uploaded some information about soil moisture and rainfall data for the state of Andhra Pradesh. This is going to be your second project. So what you're going to do, if you open the data and look at it, I'm not going to do it now. We can discuss this later. Maybe in the next class, again, we'll discuss it. The objective of this project is to estimate the infiltration rates given rainfall and soil moisture data. Okay, so I have already uploaded this rainfall data and soil moisture data on the Google Classroom. You can download that. It's provided for the whole of Andhra Pradesh. It's divided into different districts and so on. So using this rainfall and soil moisture data, and I think about 2 months of data has been provided to you. Okay, you can pick any one rainfall event, for example, if you're interested, or you do it for multiple rainfall events. Either way, it's fine with me. I'll just briefly explain what the data is. Rainfall is fairly simple. It's just given to you how much rainfall happened on every day. That's all. It's a very simple piece of information. Then soil moisture data is available at every location Okay, so let us say this is the state of Andhra Pradesh. It's a bad figure. Okay, so at all of these locations, soil moisture is measured. Okay, but at every location, soil moisture is provided at 3 different depths: 30 centimeters, 60 centimeters, and 1 meter from the land surface. So if this is the land surface, there's a sensor installed at 30 centimeters, at 60 centimeters, and at 1 meter or 100 centimeters from the land surface. Okay, so soil moisture is provided these 3 depths. So naturally, if you know the soil moisture at 3 different depths, you can find out how it is changing with time, which will give you an idea of what the infiltration rate for that kind of soil is. Okay. Now the soil moisture, the way it is provided in this database, it varies from 0 to 100%. Okay. Now you may be used to this idea that theta, what is the largest value the theta can have? It can't be greater than porosity, right? But in the soil moisture sensor will give you a number 100%, but porosity can never be 100%, right? But this 100% means if the value given in this database, if it's 100%, that means the moisture content is equal to porosity. Okay. So that's the only thing. And then whatever number, if it says 80%, then it is 80% of porosity. If it says 40%, then it's 40% of porosity. If it says 0, that means it's perfectly dry, and so on. Okay. And depending on the locations, let us say you pick a location in Guntur district, or you pick a location in Anantapur district, or you pick a location in Vishakhapatnam district, or so on. You can find out what the soil type at that location is. And if you know the soil type, you know what the porosity is. You can simply Google it. Okay. More details we'll discuss in the next class. But you can take a look at the data. It's all been uploaded to your Google Classroom. Download it. If you have any trouble, you can just send me an email or contact me. All right. Thank you very much. We will meet on Monday. All right. Bye. Take care, guys.